Hello guys, so in the first part of this lecture we talked about the forming of the depletion region, so how electrons which were majority carriers in the n-type semiconductor would diffuse in the region towards the p-type semiconductor, and holes would also diffuse towards the n-type semiconductors, and close to the surface these carriers would recombine, leaving behind immobile ions which were positive in the n-type semiconductor and negative in the p-type semiconductor. Now these immobile ions are responsible for an electric field E, which causes a drift current in the direction of this electric field, opposing the diffusion current, so an equilibrium is reached where the depletion region no longer grows. Right, so these are the concepts that we have seen, and now on this part of the lecture we're going to discuss the band diagram and how the bending of the band diagram occurs. Now one way to look at this is that the depletion region is in a sense similar to a parallel plate capacitor, where the n-type semiconductor side of the depletion region is the positive plate and the p-type side is the negative plate. So on the n-type side you have positive charges, in the p-type you have negative charges, which are the immobile ions, and therefore the n-type semiconductor side is at a higher electrostatic potential, and the negative or the p-type side is at a negative electrostatic potential. And since when we look at the band diagram we are looking at energy for the electrons, which are negative charges, this means that the side that is at a positive electrostatic potential is actually at a lower energy, and the side that is at a more negative potential is at a higher energy, and therefore the band diagram will bend with respect to the isolated band diagrams of the n-type and p-type semiconductors. So what would this look like? Well, it would look like this. The Fermi level, EF, is missing, or it's actually down here, but the Fermi level is here, right? And it's continuous, it's the same in both sides. Once this equilibrium has reached and the depletion region is formed, you know, I diffusion equals I drift, and the actual bands bend in such a way that the Fermi level remains constant throughout the depletion region. Now remember, in the n-type semiconductor you have Fermi level which is higher towards the conduction band. In the p-type semiconductor this Fermi level is actually lower, and since it has to remain at the same level in both sides, this means that the bands, the edge of the valence band and the edge of the conduction band and the bands themselves, bend throughout the region. Okay, and physically the parallel plate capacitor analogy that we said can help us make sense of this, because, well, the n-type side is at a higher electrostatic potential because it has positive charges. It would be like the plate with the positive charges in the capacitor, so it's more positive electrostatically. The electric potential V is higher, but this means that the energy is lower, so the bands in the n-type semiconductor move down because they are at a lower energy. The opposite occurs in the p-type semiconductor. Since it has negative charges, it is a more negative electric potential V, but this means a higher energy for electrons, so these bands move up, and throughout the depletion region there is a bending, this S-shape bending of the bands. So the p-type semiconductor is actually at a higher potential energy, and that is what happens. Now what we'll do is try to get an estimate of the actual function that describes the band edge or the energy throughout the depletion region. Now we have to note that in the p-n junction the charge distribution is essentially due to the immobile ions in the depletion region itself. Outside of the depletion region there is no net charge, right? So, for example, in this region right here, in the N-type side, outside of the depletion region, you have immobile ions, positive immobile ions, but the electrons, which are the majority carriers here, cancel out the charge of the immobile ions, because for each immobile ion you have a free electron, so the effective charge here is neutral. The same thing happens for holes in the p-type side. You have the majority carriers are holes, but you have negative immobile ions, and these charges cancel themselves out. Only in the depletion region you have actual charge, because since the carriers, the electrons and the holes have recombined, they left behind the immobile ions, which give a net positive charge to the N-type side of the depletion region, and a net negative charge to the p-type side of the depletion region. Okay, and on either side of the junction, the charge density can be considered uniform. So we can say that you have along the, let's say that this is the x direction. Along the x direction, we can assume that the charge density rho v, so the volumetric charge density in the N-type side, is positive because you have these positive ions here, and in the p-type semiconductor side we can assume that you have a uniform volume charge density. So rho v in the p-type side is negative because you have negative charges here. We can assume that these are constant, so the function that would describe the charge density along the x direction throughout the depletion region, well, outside the depletion region the charge is 0, right? So this would be 0, and it's uniform positive charge density in the N-type side of the depletion region. It's a uniform, constant throughout the x direction volume charge density in the p-type side of the region. So negative in this side because of the negative ions, positive in this side because of the positive ions, which we can assume are distributed uniformly throughout the region, right? And considering this, we can use Gauss's law to find out the electrostatic field and the electric potential, and finally the potential energy associated with the depletion region, or actually associated with the junction itself. So Gauss's law states that the divergence of D, the electric displacement vector, is equal to the volume charge density, and since we can consider that D is equal to epsilon, the permittivity, times the electric field, which we are representing in this way to distinguish from the energy E, right? So this is actually the electric field, this is the permittivity. We can, pass the permittivity over to the other side, dividing, and you have this expression, which was derived from this. Also, if we take into account that we are considering a problem which has only one dimension, which is x, the divergence operator will result in this, right? So only the derivative with respect to x will be non-zero, and so this is the expression that we get. This is the charge density, volumetric charge density, as a function of x, and you have dx of the x component of the electric field. If we integrate both sides of the equation, we can find the x component of the electric field. Okay, so just to be clear, this is the electric field, which will only be composed of the x component. Now we need to integrate both sides, so we have to integrate the charge density throughout the junction. Okay, so this came about by integrating this expression here. So the expression of the left hand side is Ex itself, and now we have to integrate this side. The permittivity is constant, so the only thing that goes into the integrand is the charge density itself. Now, since we know rho v, we can easily integrate. So rho v is this, right? We assume that it was uniform, so the charge density is positive and uniform in the N-type side. It's negative and uniform, constant in the P-type side, And if we integrate a constant function, you get a linear function. So because this is piecewise uniform, right? It's a constant here and here. And if we integrate a constant over x, we get c times x, right? You get a linear function for which if c is negative, this will be, you know, a rising linear function, and if the constant is negative, it will be a decaying linear function. So this is the shape of the x component of the electric field. So it will rise towards the center of the junction, the interface, and then it will go down because the electric field has to be continuous, right? So you can plug in numbers here and find this function out, but you'll get something like that. Now from this field distribution, from this Ex, right, which is the only field component, this Ex right here, we can find the electric potential V. Now how can we do this? We know that the electric field is the negative of the gradient of the electric potential. So since this has only the x component, so Ex, E is equal to, you know, Ex times the unit vector along the x direction, right? Therefore this means that this will result in Ex equal to minus the derivative of V with respect to x, which is the x component of the gradient. So you get this. And now we can integrate this. What do we get if we integrate this? Well, you get V is equal to minus the integral of the x component of the electric field, which is a function of x, as we've just seen, dx. Right? So this is what we get. And now we only need to integrate the right hand side in order to find the electrostatic potential. As we've seen, this is going to be equal to C times X, where C is negative in the p-type semiconductor, right, because the charge density is uniform and negative. So you get minus a constant times X, which is this part of the x component of the electric field, and the constant is positive here, so you have a rising linear function here, but in either case you have this function, okay? So inside the depletion region, in the n-type semiconductor, the equation for Ex is a constant plus a term of the form C times X. Therefore, if we integrate this, the result will have the form minus C1, which is the constant, times x squared divided by 2, which we get by integrating x. And the minus comes from this minus right here. Also, inside the depletion region in the p-type semiconductor, the equation for the x component of the electric field is a constant plus a term of the form minus C2 times x. So what we just discussed here, where C is C1 and minus C2. And therefore, if we integrate this, the minus will cancel with this minus here, and you will get that the V of x is C2, a positive constant, times x squared divided by 2, which you get by integrating x in that region. So if we put these two things together here, we'll get something like this, right? So in the n-type region, you have a negative parabolic function, so a parabola which goes down. Therefore, this corresponds to this right here, which is exactly a parabola, you know, going down. In the p-type side, okay, in the p-type semiconductor, we got this, so this is a right side up parabola, and therefore the function that we'll describe is this, a parabolic function like this. And the curve has to be continuous, so the potential is 0 up to here, and therefore it has to go down as a negative, you know, upside down parabola in this region, a right side up parabola here, and then it has to keep the electric potential has to keep continuous here because there's no net charge in here. If you actually plug in numbers and do the integral, you will get such a curve. So the electric potential has to be continuous everywhere. Therefore, the n-type semiconductor is at a higher V, higher electrostatic potential than the p-type semiconductor. the n-type semiconductor here is at a larger V than the p-type side. Okay, so there is the bending of the electrostatic potential. Now from the electrostatic potential we can find the potential energy. And the relation between both is this, right? The potential energy of the electron is just charge times the electrostatic potential V. If you multiply Q by V, you get the potential energy. But the charge of the electron, and when we're looking at band diagrams, the energy corresponds to the energy of the electrons, therefore we need to use the charge of the electrons here. But the charge of the electron is negative. It's minus the elementary charge E. Right, so we just need to multiply the function that we have just obtained by minus E. So we multiply by this in order to get the potential energy. And when we do this, the curve which went down for right, if we were looking at V, the curve would look like this. If we multiply this by, minus by a negative constant, we get the green curve right here. So this is the actual potential energy that we get, which is just the red curve multiplied by a negative constant. And therefore we see the shape of what the energy has to look like. So therefore the curve for the potential energy has a piecewise parabolic dependence on x, as did the electrostatic potential. So the n-type semiconductor is at a lower potential energy than the p-type semiconductor. The n-type semiconductor side is at a lower potential energy than the p-type semiconductor is, and the overall potential energy distribution looks like this. So the function we have just found is the one that describes the behavior of the conduction and valence band energies as a function of x. Okay, so this curve, because it describes the potential energy along the junction when the depletion region is formed because of the electrostatic potential of the depletion region, this is going to be the overall shape of the band edges, right? So the conduction band edge will look like this, the valence band edge will look like this, and the whole bands themselves will be bent like this, because, well, once the depletion region is formed, you have this electrostatic potential, and the potential energy is related to the electrostatic potential. So the whole band diagram is bent in such a way. We have just found, in more or less a hand-wavy way, mathematical expressions that describe this bending of the bands. But this is actually what happens. So when you put the two semiconductors together, the bands will bend. The Fermi function will remain constant throughout the depletion region and the whole junction, but the bands themselves will bend. Okay, this is an important phenomena here that we need to keep in mind and understand. Okay guys, so thanks very much for your attention, and I'll see you on our next lecture.